First off, a big thank you to the organizers for putting together a nice program. It's nice to follow these talks because they set the stage nicely for another setting that involves online matching. If you didn't look closely at the schedule, you might be surprised that there's a bonus talk in this session. So thanks for sticking around. So my name is Scott Rodilitz. I'm just starting as an assistant professor at UCLA's Anderson School of Management. I'm excited to share some joint work with some amazing co-authors, Vahideh Manshadi, who's a professor at Yale, Daniela Saban, who's a professor at Stanford, and Akshaya Suresh, who's just finished her third year as a PhD student at Yale. So this work stems from a collaboration with Volunteer Match. So I'll start by giving you some background on that platform. If you're familiar with Upwork or TaskRabbit, it's similar, but instead of matching temp workers and jobs, it matches volunteers with volunteer opportunities. It has over 100,000 opportunities posted on the platform, and it gets more than 1 million monthly visitors. And these visitors predominantly use the site for two key purposes. So first, they use Volunteer Match to provide them with a list of recommended opportunities for them to volunteer their time. So maybe they'll search in a particular location, maybe they'll filter based on causes, and they'll get a list of opportunities that might be good fits. And then they'll also use Volunteer Match to facilitate their connection to these organizations. So once they've picked an opportunity, they can click this I want to help button and be connected with the nonprofit. So we're going to refer to these visitors as internal traffic because they interact with the internal recommendation algorithm on the platform. But it represents only about 70% of traffic on Volunteer Match. The other 30% of traffic is what we refer to as external traffic. And these visitors bypass the platform's recommendation algorithm and instead directly sign up for an opportunity. So they use the platform only to facilitate this connection. And the way these types of visitors come about, it can arise from a variety of ways, but the main ones include clicking on advertisements on LinkedIn or posts on Facebook or something of that nature. OK, so that's the setting we have in mind. One interesting feature of this platform is also that each opportunity, of course, has some finite capacity for volunteers. Their needs are not infinite. So in this example, this 5K walk run needs about 50 volunteers. So with that in mind, let's take a look at what matching outcomes on this platform look like. So here is a histogram of a random sample of 100 opportunities, each with a capacity of 10. And my hope is that the first thing that you notice is that this distribution is very uneven, right? There's some organizations that are getting no signups. There's some that are getting way more than what they need. And I want to emphasize that this uneven distribution is bad for everyone. So of course it's bad for the organizations that don't get any signups, but it's also bad for those that get a lot, right? It overburdens the organizations, and it wastes volunteers' time. They're not being used effectively, and that can be discouraging. So we want to think about ways in which we can rectify this. So to that end, we can make a couple of observations about why this is happening. The first is that the amount of external traffic across different opportunities is very heterogeneous. There's some that get a lot of external traffic, in fact, more than what they need in total. And then, of course, there's many that don't get any. And yet, in combination, there's a lot of internal traffic that seems to get directed to opportunities that certainly don't need it. And so that suggests that maybe there's something suboptimal going on with how these recommendations are being provided. So in this talk, we're going to think about how platforms should design their recommendations, knowing that traffic might be multi-channel, given the goal of maximizing what we're going to call useful signups, or signups up to the capacity of each opportunity. OK, so with that in mind, before getting into the model, I want to take a brief moment and just mention that this, it's motivated by Volunteer Match. But of course, we think multi-channel traffic arises in a variety of contexts. I've provided a couple of examples for you here. So if you're familiar with Donors Choose, it's a way to donate to classroom projects so that they get funded. You get some people arriving who use a search algorithm on the site, and you get others who arrive via a direct link, maybe through a school website. Etsy, you're probably familiar with, is a marketplace for sellers of bespoke goods and prospective buyers. You can search for goods on Etsy, but you can also arrive at a particular seller's page via a link on Instagram. So,
just a clarification. So you
sure.
assume the external traffic cannot be rerouted by...
Yeah, good. I'll get to the model specifications, but you're totally correct. That's exactly what we'll assume. So broadly speaking, this builds on a literature on modeling what we think of as realistic features of traffic on matching platforms. So there's some nice papers in this stream, a couple of older EC papers. Happy to talk about any of these offline, but in the interest of time, let's get into the model. So as you might expect, given the session so far, we're going to think of this as a variant of online matching. So we've got a set of volunteering opportunities, which are offline vertices. We're going to assume for the purposes of this talk that they're always in the system for the time horizon that we have in mind. That's something that we can easily relax. And these opportunities have some known capacity for volunteers. Now the volunteers are going to arrive sequentially, one in each time period. But they're going to be one of two types. They're going to be external traffic or internal traffic. And exactly as was suggested by that clarification question earlier, when external traffic arrives, the platform doesn't do anything. It simply signs up for the opportunity that it has in mind and takes 1 unit of capacity from that opportunity. Internal traffic, on the other hand, we're going to model in what I'm going to describe to you a very simple way. In the paper, we think about how to extend this much more broadly. Happy to talk about that offline, and I'll touch on it a little bit at the end of the talk. But we'll consider a very simple model for internal traffic. It arrives. The platform observes which opportunities it's compatible with. The platform recommends a single such opportunity or no opportunity at all. And then the volunteer signs up for the recommended opportunity deterministically. So for example, the platform recommends opportunity 3, and the volunteer signs up. So you can think of external traffic as a special case of internal traffic with degree 1. That's fine. And that's a good way to think about it technically. So our goal is going to be to design an algorithm that maximizes the amount of filled capacity, either from external or from internal traffic, without any knowledge of the arrival sequence. So we're going to allow for any arbitrary mixing of internal and external traffic and any sequence of compatibility structure for the internal traffic. And of course, what we're going to use is the somewhat standard approach, which is the competitive ratio. I won't go into details about what that is. I think the previous speakers have done a great job with that. I'll just mention that the benchmark that we have in mind here is this optimal clairvoyant algorithm that knows the arrival sequence in advance, that knows this compatibility structure in advance. And so with this in mind, it's natural to ask, what do we already know about the problem? And to a certain extent, we already know everything that we want to know, thanks to a very nice paper by Mehta, Saberi, Vazirani, and Vazirani about 15 years ago. So in the absence of external traffic, the best competitive ratio that we can hope for is 1 minus 1 over E. And that is, in fact, achievable by their algorithm, which I'm going to, for this talk, refer to as MSVV to keep things simple. So this is assuming capacities are large. That's an assumption I'm going to stick with. It's something that's necessary when you want to run deterministic algorithms in this context. OK, so that's good to know. What else are we going to do here? Well, the second fact that I want to draw your attention to is that if all traffic is external, we can actually do much better, and somewhat by default. No matter what we do, we're not making any decisions, so we'll do just as well as this optimal clairvoyant solution, and we'll get a competitive ratio of 1. So what we want to get at in this talk is what can we hope to achieve when we're somewhere in between these two extremes? And to get at that question, we're going to refine this notion of a competitive ratio, and we're going to parameterize it by beta, where beta represents the fraction of capacity that can be filled by external traffic. We're going to refer to this as the effective fraction of external traffic. And the key idea is that more external traffic limits the number of mistakes that an online algorithm can make. So we would expect to be able to get improved performance as beta increases. OK. So with that in mind, I'll introduce our algorithm, and I'll introduce our main results. To help with this, I'm going to start with a warm-up setting that can build some intuition behind the design of our algorithm and behind the results that we get. So we'll start by thinking about a setting where all the external traffic arrives first, and then all the internal traffic arrives. This should be an easier setting, right? We're restricting the adversary in terms of what the arrival sequence can look like. So we know 2 points on this potential competitive ratio curve. We know that when there's no external traffic, the best we can hope for is 1 minus 1 over E, but that is achievable. And when everything can be filled by external traffic, we know that the best we can hope for is 1, and that is, of course, achievable. So what happens in between those two extremes? Well, first, it's pretty easy to establish an upper bound that's a linear combination of those 2 points. But somewhat surprisingly, if you run MSVV on the entire sequence of arrivals, you can't achieve this upper bound. In fact, MSVV is upper bounded by this red curve. Instead, what we propose is an algorithm called adaptive capacity, which does achieve this linear upper bound in the limit of large capacities. So how does adaptive capacity work? Well, it's pretty intuitive in this warm-up setting, which is why we started here. So when external traffic arrives, it fills some amount of capacity for each opportunity. We look at these reduced capacities, so what's left, and then we run MSVV on those reduced capacities. And that's what gives us this linear combination. Now, we can't do that, of course, in a general setting where the external and internal traffic are arbitrarily mixed. So we're going to do the next best thing, which is adaptively reduce capacities on the fly as external traffic arrives. So to briefly formalize this, we're going to have two counters for each opportunity, one that represents external traffic, one that represents internal traffic for each opportunity. When external traffic arrives for an opportunity there's nothing to do, we increment the counter for that opportunity. When internal traffic arrives, we first decide which compatible opportunity to recommend based on this function. We then increment the counter for that opportunity. And I want to talk a little bit about this function. First, it's a decreasing function of both external and internal signups. But it crucially distinguishes between which channel the signup came from. And this is the big difference between what we're proposing and MSVV. So MSVV treats all signups equivalently, whereas we reduce signups from external traffic from the capacity of the opportunity. And this allows us to achieve good performance in the warm-up setting, and as I'll show you in just a second, allows us to achieve better performance in the general setting. Before getting there, I want to mention one thing. There's something that's not present on this slide, and that's beta. So nowhere in the description of the algorithm does beta appear, which is really nice. We don't need to know how much external traffic there is when we run the algorithm. Often knowing beta up front is impractical in a variety of contexts. OK, so I'm going to not get into as many technical details as maybe some of the previous talks. I'll just give you a high-level overview of some of the main results in the paper. So first, an upper bound. No algorithm is going to achieve a better competitive ratio than this solid blue curve. So you'll note we no longer can achieve this linear combination. That's because we can have an arbitrary mixture between external and internal traffic. But in fact, adaptive capacity is able to achieve as a lower bound this dotted blue curve, which is pretty close to the upper bound on any online algorithm. Whereas MSVV is upper bounded by this dotted red curve, which, as you can see, does have some significant separation for particular values of beta, at least. And the main thing that I want to highlight from these three main results is that adaptive capacity is near optimal for any amount of external traffic without knowing what that amount is up front. OK. So I'll allude briefly to the proof details. So we use this path-based pseudo-rewards approach, which one of the previous speakers, Rajan Udwani, and his co-authors have been writing about recently. It's a really nice technique. It helped us a lot to separate the impact of internal and external traffic. So I encourage you to either check out what we do in the paper or look at some of his earlier work if you're interested in that sort of thing. I promised I'd briefly mention some generalizations to approach more practical settings. So in the paper, we do consider settings where there's stochastic rewards. So instead of deterministic signups, you get stochastic signups. And also, of course, ranking settings where you provide a ranked list of opportunities and you have some choice dynamics from the internal traffic. In many settings, we can break the 1 minus 1 over e barrier using our algorithm, which naturally generalizes. And feel free to ask me or check out the paper for those more intricate details. With that in mind, we can return to our motivating example of volunteer match, which has a lot of those practical considerations. And we can quickly look at a case study. So we used data from volunteer match to generate an instance. So we took a random sample of opportunities. We estimated conversion probabilities based on opportunity features. We borrowed directly the traffic pattern from data, both the mixture of external and internal traffic, as well as their relative proportions. So you'll note that the effective fraction of external traffic is only 19% in this case study. That's in part because it's a somewhat undersupplied system in terms of volunteers relative to the 30% of traffic that's external. And we don't have data on choices that volunteers make, so we used a kind of simple cascade model to model their choices. Just high-level results from this plot. Adaptive capacity does quite well, much better than its theoretical guarantee for this regime where there's not that much external traffic, even compared to an LP upper bound on opt. It performs similarly to MSVV, which is what you might expect when external traffic is not that prominent. And it does much better than this current practice that the volunteer match uses, which is a pretty simplistic policy. So to sum up, we introduced a new model for what we think is a pretty important phenomenon on a lot of platforms, which we call multi-channel traffic. We designed this adaptive capacity algorithm, which is near optimal regardless of the amount of external traffic, even though it doesn't need to know it in advance. It provides better guarantees than common alternatives like MSVV, and it does so by incorporating source. It naturally generalizes to complex settings, at which we showed we can also achieve strong performance in the case study that I just showed you. We think there's some nice ways that you can go from here. One in particular that we're excited about is an experiment that we're running on Volunteer Match's platform with an algorithm that's motivated by this work. So I hope either myself or Akshaya or one of our co-authors shares more about that with you in the future. And we think there's some interesting theory directions you can take this if you're interested in different objectives or if you're interested in how the platform might control this external traffic in a clever way. But for today, that's all I have for you. Thanks so much for sticking around, and happy to take questions if we have time. I know the session is running.
Okay. Questions? Yes, Rob.
Very nice.
Sure.
Very nice talk, this talk. So, quick question. So if you knew the parameter beta, couldn't you just simply reserve beta fraction for the external traffic and anonymously on the rest?
Good. So beta. So Rod asked if we knew beta, essentially how would that help us? What would that give us? So a few things. If we knew beta I, where beta I is the amount of external traffic for each opportunity, that would basically get us back to this setting where external traffic arrives first. So that's a much more reasonable setting, but it allows us to basically predict how much capacity is being filled by external traffic. If you have some concentration bound around that amount, you're going to get this linear upper bound and matching lower bound by adaptive capacity. If all you know is the average beta, so like the total beta, it doesn't help you at all in the setting that I was describing, right? So this is the upper bound that we have. The lower bound on adaptive capacity, which doesn't use beta, is essentially identical. And I should say we think that this gap is from the analysis, not from any shortcomings of the algorithm. There is the possibility that knowing beta helps in extensions where we have stochastic rewards. It's plausible if beta is very high there, you could design a slightly different algorithm that does badly in the absence of external traffic, but that can do slightly better than what we guarantee. Happy to talk about that more offline.
And then I think if you knew beta, you can easily get beta squared plus 1 minus 1 over e times 1 minus beta, which is actually you get a coin equal to beta. And then if the coin flips heads, go with the external traffic, otherwise just run STV. But then you are getting beta plus 1 minus 1.
Yeah. I think your point is like knowing once beta is sufficiently large, you can have better guarantees than 1 minus 1 over e for sure. But I think what you're proposing would be below this lower bound curve that we have. Yeah.
Any other question? All right, let's thank all the speakers.